Hello everybody, this is Math 145, day 12. We're looking at lesson 10, which covers word problems. Love them or hate them, they are definitely a must cover part of the syllabus. The whole thing would be just pointless if it didn't have the connection to reality. So we're looking at these word problems, and I'm hoping that you will discover, like I did, that the problems in this lesson 10 are actually fairly simple. They're on the level of this ladder problem that I did when we did first trig ratios. So in particular, it's not the quite hard identities that we learned in lesson 9. We'll get to those later, but right now it's sort of regressing a little bit, and I'm going to show you a bunch of them because just making sense of the text is a challenge in itself. So, the pendulum. Sorry. A pendulum has length, say 50 centimeters. And, well, it swings left or right, as pendulums do. Let's say it swings 25 degrees to one side. How far does the tip of that pendulum rise from the rest position? So the clue about that word rise means just the vertical distance. How much higher is it in that position than in the rest position? That's not the same as the distance that it travels. And before we solve this, we should just talk about general strategy. It applies to most word problems. First thing is give names to the relevant quantities. And I mean one letter. Names to relevant quantities. In particular, the quantity that you want to find, that always needs to have a one-letter name. But sometimes there's a elaborate word problem and you have a lot of quantities and they all need their separate names, except if one quantity is very easy to express in terms of another quantity. If you have a radius of a circle, then you don't need a name for the diameter and vice versa. But in short, give names. Next thing, if it's a word problem that has geometry in it, make a sketch. Keep it simple. Don't do elaborate drawings. Keep it two-dimensional if you can. Don't draw three-dimensional wonderful things, but make it neat and make it big. No squeezing into a tiny corner of your paper. Then you read the problem again and translate every clue into an equation or inequality. Well, and the last thing is you need to solve those equations and find that quantity you're looking for. All right. Back to the problem, pendulum. So make a sketch. Vertical is the way that the pendulum hangs in rest position, and then it swings 25 degrees say up to here. And because it's supposed to be either a metal rod or a string that is being kept straight by a weight at the end, that would be traveling on a circle. Keeps the same distance from the point where it's attached at the top. And the radius of that circle, that's given, that's the 50 centimeters. And the angle is the 25 degrees. Now, what do we want to find actually? How much does the tip of the pendulum, which is that point, consider that weight at the tip at the point, how much did that rise? And you could sketch this distance as a vertical line from the horizontal, but it's actually better to sketch it over here and consider the line that the pendulum makes in rest position as giving you the x-axis. You can't put a full grown coordinate system on the whole thing, but we can also just work with these distances and call that triangle, say, A, B, C. So the line BC is vertical. The line AB is horizontal. So we have a right angle here. And it's a right triangle with hypotenuse 50. One angle is 25. We still need to give a name to the quantity that we want to actually find. How about X? So X is that little line segment down here. I'll also give that point of the pendulum, the tip of the pendulum in rest position, a name, call it D. Might think again, why is there a right angle at B? It's because the line segment BC is vertical and the line AB by definition is horizontal. Because we are transporting this vertical line segment here which is a little awkward, over to the center horizontally. It's our decision to do that, and so we can say we're making a horizontal movement, and therefore the line AB is perpendicular to the line BC. We have a right triangle. X is what we want to find. So we got labels for the corners, for the points. That means we can also express the sides of that triangle. And we should make it clear the distance of 50 applies to that line all the way down to D. So that's where we really see that 50. Put it over here. Now let's solve the whole thing. We need to deal with the triangle ABC. And because it's the right triangle, we can say the leg BC has length 50 times cosine of 25 degrees. It's the near leg. And the line DC has length 50 because that's given. And the quantity that we're looking for, so that rise, that is length of DC minus length of BC. That's 50 minus 50 times cosine of 25 degrees. If you calculate that with a calculator, make sure you convert those degrees to radians, because by default, your calculator expects input for trig functions as radians. Oh, factor out 50. 50 times 1 minus cosine of 25 times pi over 180. That's the conversion factor to radians. Hack that into a calculator, and you should get roughly 4.68 centimeters. Only at the very end do we go back and mention what the units are. All right, so I talked a lot, but the problem itself, trig-wise, really is not that hard. Standard right triangle kind of deal. Another very nice problem, which is also coming back to right triangles, is the problem which in the book is done with a flagpole. I like to do it with an entire building. Cast a shadow. Of length 120 feet, let's say, at some moment in time. And the angle of elevation of the sun at that time, seen from the tip of the shadow. Is I did 25 degrees and 30 seconds, just so we practice those weird old-fashioned ways of measuring angles sometimes. How tall is the building? All right. I like to start with my sketch to see what's what. So, building. And then it casts a shadow. Which makes this angle with the ground. And that is the angle of elevation of the sun, because if you're looking from the tip of the shadow, what's here, the base of that right triangle, sorry, base, it's the longer leg, we should say. Yes, also base, but the hypotenuse is the line of sight. When somebody is putting their eye right down there, they should look straight into the sun. Sun sends out rays in all directions, but the ones that limit the shadow, that's the one that goes just across the edge of the building. The others either do not limit the shadow or they are blocked by the building. So we are given the length of the shadow, that's 120 feet. And we are given this angle that I want to call theta. And what we are after, needs a one-letter name, is the height of the building, right here. Call it h. After you've made that sketch, you understand what's going on. The rest is a right triangle with the shorter leg being h and longer leg is 120. And this angle theta, so the tangent of theta is h divided by 120. Opposite leg divided by near leg. And we can solve that for h. H is 120 times the tangent of this angle, 25 degrees and 30 seconds. How do you enter that into a calculator? Answer is 60 seconds. Sorry, I was talking of seconds. I meant minutes. The thing is degrees, then minutes, and then seconds. And that was the entire time. This one little dash here means minutes. So 60 minutes make 1 degree. 30 minutes form half a degree. So we should enter 25.5 degrees. And then convert it to radians. And that comes out to roughly 57.2, and we're talking feet. Note 30 minutes is a unit for angles and minutes, not time here. And that equals 1/2 of 60 minutes, which is 0.5 degrees. All right. 2 examples, and the other ones are really not harder than that, I think. So go look at them. They're good examples, but this video clip has enough. I think it's only worth anything if you work them with paper and pencil and follow this without reading ahead. See, after you read the problem, could you have done that? Do them for yourself, and then you can get something out of them. You should be able to do all of these in lesson 10.